Welcome to this lecture series in number theory. In this lecture, we'll finally answer the question of the existence of inverses as to when exactly we can say that the inverse of a given integer exists modulo another given integer. So we need to recall a bunch of things, and here is one definition. Fix a positive integer n and fix a in z mod nz. So again, I'm assuming that you know what this is by now. This is the set of all the remainder classes modulo n. Okay, so then for each element x of z mod nz, we define the trajectory of it as this set. So you can think of it as starting at x, and then at each k, or you can think of k as the time, even though it is not, the set is not like integers or anything. Still, you can think of it as advancing by a. So you have x, then you have x plus a, you have x plus 2a, and so on. All these things are here. And here when we have written plus, we are adding elements of z mod nz. Both x and ka are elements of z mod nz. The elements of z mod nz can be multiplied and they can be added. We discussed these things at length. So that's the trajectory, and we also saw some examples, some concrete examples where we drew the things out. So I encourage you to check them back if your memory is foggy. Okay, and we saw one property which we termed as the equipartition theorem. So fix a positive integer n and a in z mod nz. Then for any two elements x and y of z mod nz, either their trajectories are equal or they do not intersect. Okay. Further, any two trajectories have the same size. So this shows that the trajectories partition z mod nz because everything has to be in some trajectory and no two different trajectories intersect. Right? And the second clause now shows the equipartition, that, since each trajectory has the same size and the trajectories partition the set z mod nz, we can say that these together form an equipartition of z mod nz. So that was the equipartition property that we proved probably 2 lectures ago. Okay, then we also saw a factoring property. Again, fix a positive integer n and s be any set. And suppose f is a map from the integers to s with this periodicity property. So f of x plus n is f of x for all x in z. Then we claim that there is a unique map f bar from z mod nz to s as shown here, such that this diagram commutes, meaning either you just directly apply f or you go via this route, where the vertical map is the natural projection map, which does what? It takes an integer and outputs its remainder class modulo n. Right? So this diagram commutes. This was a very simple fact, even though we took a long time, or we developed something called set theoretic quotienting before proving it, even though this is a really, really elementary fact. Okay, so we will employ all of these things, and now let us proceed. Some problems for practice. And now let us get started. So here is one definition that we need in order to characterize the notion of the existence of, the notion or the fact about existence of inverses. So suppose we have two integers a and b, then we say that an integer d is a common divisor of a and b if, as the name suggests, it divides both a and b. It's a common divisor if it is a divisor of both. It's a very simple definition. Okay. We say that a and b are relatively prime if the only positive integer or the only positive common divisor is 1. So note that 1 is always a common divisor. You pick any two integers, of course 1 will divide both of them. We will say that the two integers a and b are relatively prime if the only way you can find a common divisor, the only positive common divisor that you can find is 1. Right? So they do not share common divisors, so to say. Of course, if 1 is a common divisor, -1 is also there, but that's kind of spurious. Let's look at some examples. So here is a very simple example. 3 is a common divisor of 6 and 9 because it divides both of them. Right? And now here is an example of relative primality. 4 and 9 are relatively prime. None of them are prime numbers. When we say A and B are relatively prime, we are not talking about the primality of A and B or anything. It's just that relative to each other, they behave like they are like prime to each other because they do not share any divisors, so to say. Okay, so that's one example of relative primality, and a more general or sort of class of examples is if you pick any positive integer n, then it will be relatively prime to n plus 1. So why is that? Let's try to explain that. Why is it that n and n plus 1 are relatively prime? It's because suppose d is a divisor, common divisor of n and n plus 1, where d is a positive integer. We want to show that d is equal to 1. Right? But if d divides both of them, then d divides their difference. D divides their difference, so this means d divides 1. And since d is positive, this means d is equal to 1. Right? So if you take a positive integer which is a common divisor of n and n plus 1, you will see that it divides 1 and hence it is equal to 1, and therefore n and n plus 1 are relatively prime. This was intuitively obvious. How can two integers very close to each other share a common divisor? That just doesn't sit well with our intuition. But here is a proof of it. Okay. Here is another class of examples. Suppose p is a prime number and n is some positive integer such that n is not divisible by p. Okay. Then we claim, then this is more like a lemma, then p and n are relatively prime. So why is this? Well, recall we previously proved that if a prime number divides the product of two integers, then it divides at least one of those two integers. Okay? So if you, or maybe we don't need that, let's see. So suppose d is a common divisor. So suppose d is a positive integer and it divides p and it divides n. Yeah, so you actually didn't need anything that I said about prime dividing the product of two integers or anything. Just pick a common divisor, which is positive. Since it divides p, there are two possibilities for it. Either it is equal to p or it is equal to 1, because a prime number has only two positive divisors. If it is equal to p, then we would have p divides n, and that would contradict the assumption that p doesn't divide n. So therefore d is forced to be equal to 1. That's it. So whenever you have a prime not dividing some integer n, the prime and that integer are relatively prime. Hopefully these three examples have shown or given you some intuition about this concept. Okay, and here is the main theorem that we want to prove today. So suppose we have two positive integers, although we didn't really need to have a as some positive integer. So in fact, even n is not required to be a positive integer, but let's not change that. So let a be any integer and n be a positive integer, although n also could have been negative. It's just that n couldn't have been 0. If you take n as 0, then it's not. I mean, it's you're basically asking for division by 0 and those kinds of things. So anyways, let's just keep n as positive. So then this congruence, ax congruent to 1 modulo n, is solvable if and only if a and n are relatively prime. So this is what we want to prove. In other words, a admits an inverse modulo n if and only if a and n are relatively prime. So the criterion for existence of inverse is precisely that the two integers in question should be relatively prime. Now, we have already proven a special case of this. We showed that if n were a prime number and a was not divisible by p, then a admits an inverse modulo p. This is what we proved using the equipartition theorem. And if you just look at this statement, it shows you that if you have a prime and some integer a not divisible by p, then a and p are relatively prime, and hence this theorem generalizes that conclusion, right? So what we proved about the specific case of prime modulus is now generalized by this theorem. Okay, and here is an if and only if. I mean, this is a characterization. So what it says is that if a and n were not relatively prime, then there couldn't possibly have been an inverse. Okay, so this is a full characterization of the existence of inverses. All right. So this is what we just stated. This is what we just stated in the previous slide. This is our goal. And let me show you at least, one. Yeah, let me talk about this a little bit. We will prove it, but let me say at least one direction. Let me give the proof in one direction. So suppose A has an inverse modulo n. Okay, so then we want to show that A and n are relatively prime. So then there is an integer x such that this congruence holds, right? But what is this congruence? Let's unravel the definition of a congruence. So therefore, there exists some integer q such that ax equals 1 plus nq. Correct? Just unravel the definition of a congruence, which means ax minus nq is equal to 1. Okay, but now note that if a and n had a common divisor, let's say d is a common divisor. So say d is a positive integer, which is a common divisor of a and n. What do we want to do? We want to show that d is equal to 1. That is what it means to show that a and n are relatively prime. Okay, but since d is a common divisor of a and n, it divides the LHS. If it divides both a and n, it will divide the LHS, and hence it divides the RHS, which means d is equal to 1 since d is positive. So that proves this direction. Right? Now for the other direction, suppose a is relatively prime to n, then we want to show that a has an inverse modulo n. This is the hard direction. So suppose a and n are relatively prime. So the proof in this case is the rest of the lecture. So this is what we'll prove in the rest of the lecture. But here I want to mention that the reader is encouraged to skip the rest of the lecture. Encouraged to skip the rest of the lecture, especially if this is the first time you are learning elementary number theory. Another reason to skip this, I mean, why am I asking you to skip this? It's just because the proof is a little bit complicated. It is not complicated at the heart of it, but when you're reading these things for the first time, it might look horribly complicated, especially because of the notation. Okay. Another reason why I'm asking you to skip is that we will give a different proof of this statement. We will give a very simple short proof of this statement later. And by later, I mean maybe in the next few lectures, in the next module somewhere. So there is a very short and simple proof of it. Now you may ask, why am I, in that case, giving a complicated proof? Well, because I think this complicated proof explains a lot. And it has an added advantage that it introduces us to a lot of interesting mathematics. The kinds of proofs or the kind of lemmas that went into the proof that I'm going to discuss today, those have taught us a lot, in my opinion. So that's why I want to discuss that. But for the first time for the reader who is doing these things for the first time, it's probably a good idea to not read this proof now. You can come back to it later. Okay? All right. So there is this one corollary that I want to discuss. And this was not meant to be skipped. What was meant to be skipped was the next slide and so on, but not this corollary. So what is this corollary? It says that if A and N are relatively prime, and N divides the product of A and B is some other integer. And yeah, when I say A and N are relatively prime, I already mean that A and N are integers. Okay, so suppose N divides A times B for some integer B, then N must divide B. Okay? So this is a generalization of the fact that we proved about primes. If a prime divides the product of two integers, then it has to divide one of them. Right? This generalizes that fact. Think about it. Think about why this generalizes that fact. So let's see why this is true. We will use our main theorem. So if A and N are relatively prime, then we know that there is X such that this congruence holds. We know that there is X such that this congruence holds. Multiply by B on both sides. We get ABX is congruent to B modulo N. But AB is divisible by N, and hence it is 0 modulo N. So we have B is congruent to 0 modulo N, and therefore N divides B. Right? So that's a very nice corollary that we draw out of this theorem. Okay, hopefully now the characterization, the statement is clear. The statement is more important than the proof for us. The proofs are important, but as I said, this particular proof can be skipped. Okay, so let me now proceed. Yeah, so before we go into the proof, here is a small calculation which motivates the proof, at least to some extent. Just like we motivated the first equipartition property, or what we called the equipartition property, not the first, but the equipartition property. Just like we motivated that using examples, this one also is motivated by examples, and here is one. You should compute more, but I'll just show one. So recall this picture. If you have N as 15 and A as 6, and when I say 6, this is the remainder class of 6 modulo 15, but that's okay. And here on the periphery of the circle, we have written all the remainder classes modulo 15. And these objects, these star-shaped things, are trajectories. So this is the trajectory of 0, the red thing. Then we have the trajectory of 1, and then we have the trajectory of, 2, something I'm not able to track. Anyway, so we have these trajectories, and here is the observation. So let's isolate the three trajectories separately. This is the red trajectory, the blue trajectory, and the gray trajectory. And here I have listed out all the integers. So this is all the integers. And now here is what we are going to do. We pick some integer, let's say 3. We see which trajectory does 3 modulo 15 lie in, red, blue, or gray. Okay? So we have the integer 3. Think about the remainder class of 3 modulo 15 and ask, which trajectory does it lie in? And we see that it lies in the red trajectory. Here it is. So we color 3 with the color red. Right? So we do this for every integer. So that's kind of a boring thing to do, but let's do it. So here is 1. 1 is in the blue trajectory. So we will color it blue. 2 is in the gray trajectory. So we will color it gray. 3 we have already colored. What about 4? 4 is here in the blue trajectory. 5 is in the gray trajectory. 6 is in the red trajectory. And let me now fill the rest. You can verify. Okay, so that's it. And here is something that we note, something that you can prove here is that whatever is the color of 0, same is the color of 6. Whatever is the color of 1, same is the color of 7. Whatever is the color of 2, same is the color of 8. And so on. Whatever is the color of the integer x, same will be the color of the integer x plus 6. So if f is the color function, f is the function which takes an integer and asks or tells us what is the color of that integer, then f is a function with period 6. It has in fact an even smaller period. It has period 3, but forget about that. It has period 6. F satisfies this equation for all integers x that you can verify, and that we are kind of seeing when we explicitly write down the colors. Color of 0 is same as color of 6, 1 is same as color of 7, and so on. So by the factoring property, we get a function from z mod 6z to the set of all the colors, or you can say the set of all the trajectories. So this notation, this is the set of all these trajectories where the 6 is A and 15 is N. Right? So this is a set of size 3. 1 corresponds to the red. I mean, it has this set of elements, that is one element here, right? I mean, all I'm saying is that this is the set of all the trajectories, but there are only 3 trajectories, and those 3 things are what this set contains. So there is a function from z mod 6z to this set that we obtain by the factoring property. Because of the periodicity of this color function, we get such a map. And another thing that you can observe here is that the fibers of, let me call this tau bar, the fibers of tau bar form an equipartition of z mod 6z. The fibers form a partition. That's not a problem, because fibers always partition the set. You take any function, the fibers of that function will partition the domain. I mean, the non-empty fibers will partition the domain. What we are saying is that they form an equipartition, meaning any 2 fibers have the same size. And if you just focus here, you will see why is that. You just focus on the kind of the z mod 6z aspect of it. Right? These are the representatives of z mod 6z. So this will correspond to 1 fiber, this will correspond to 1 fiber, and that will correspond to 1 fiber. There will be 3 fibers in, of this function tau bar. And all of them have the same size, namely 2. But that's a little bit sloppy because these are not really elements of z mod 6z. However, that is essentially true, just a pedantic notational difference is there. So just verify the statement. Maybe my talking is a bit confusing at this point. Just verify the statement that the fibers of tau bar equipartition z mod 6z. What is tau bar? How did we create this function tau bar? First, we had this function tau, which I was so far calling f, but now I want to call it tau. So tau is the function which assigns colors to integers, or you can say tells us which trajectory a given integer lies in. You pick an integer 0, consider its remainder class modulo 15, ask which trajectory does it lie in? It lies in the red trajectory. So that is the color that you assign to it, or you can also say that is the trajectory that you assign to it. This is the set of all the trajectories. Similarly, you do it for all integers, and then you will find that this function has periodicity with period 6. It's a separate matter that it has even smaller period, but it has period 6. And therefore, you get a function tau bar by the factoring property that we discussed. You get a function tau bar from z mod 6z to the set of all the trajectories, which has what property? Which makes this diagram commute. So that was obvious. I didn't mention that. It makes this diagram commute, right? Where the vertical map is the natural projection. And then I want you to look at this statement that the fibers of tau bar form an equipartition of z mod 6z. Once you realize this, or once you work this example out, this is what we are going to prove in general. And that will be the second equipartition property. We have already proven an equipartition property here on this side, but the second equipartition property is on this side, on the left side. And when we use the first and the second equipartition property together, we will be able to give a proof of the main theorem that we want to do. So that is what is going to happen next. So let's proceed. All right, so what we just saw in this example is now we are going to prove in general, and I will refer to this phenomenon as the second equipartition property. So what are we saying? Fix a positive integer n and an integer a. So note that a is not in z mod nz, it is a genuine integer. And this will cause us notational nightmare, but what can I do? So define a map tau from the set of all the integers to something. What is that something? So let's first write that down. So let script tan be the set of all the trajectories that you get when you advance by a modulo n. So this is the set of all the trajectories when you vary over elements of z mod nz. Let me write a y here. That's better perhaps. Again, it will be a notational nightmare no matter what I do. So we have to be prepared for it. Right? That's the definition of this guy. Now you may ask, what is this? Well, this, I should have technically written it not like this. I should have written it like this. That's what I should have written, because so far we have been notating it as such. This thing was not a genuine integer. This thing used to be a remainder class. But now since a is a genuine integer, when I write an a here, you may get confused. But that's okay. Get confused. I mean, don't get confused, but be aware is what I meant to say. So if I want to explicitly write this down, what is this? This is equal to y plus k times the remainder class of a, where k could be anything in z mod nz, which I could have also written as, this is fine. That's what it is. So that's what that is. Right? This is a subset of z mod nz. Don't rush this proof. I want to emphasize all of this will require you to be very vigilant with the notation, as one should be in mathematics in general. And try to, if you are here, if you did not choose to skip the lecture, if you're here, then try to not rush this proof. It will be rewarding. All right, so this is the set of all the trajectories when you advance by a modulo n, and this is a subset of z mod nz. You should keep an example in mind. In the previous slide, we saw an example. You should run this proof with a particular example in mind for better understanding. That is true of most proofs. Okay, so now define the map tau, which picks an integer and outputs a trajectory. It is defined this way. You take an integer x and just output the trajectory of the corresponding element modulo n. Right? This is the This is the remainder class of x modulo n, just like this is the remainder class of a modulo n. Okay, and we are just outputting the trajectory of x modulo n. Right, so that's the map tau. We have chosen the symbol tau because tau is like t is like trajectory. Okay, just a definition. But now here is the thing. We note that tau has this periodicity property. It is periodic with period a. It could have a potentially smaller period, but it certainly has period a is what we claim. So let's prove that claim and then see the rest of the statement. This is not the equipartition property yet. This is just part of the whole package. So what is the reason behind the blue statement? Okay, so we just want to show. So fix an integer x. Want to show that tau x is equal to tau x plus a. Right? But what is tau x? Tau x by definition is the trajectory of the remainder class of x, and tau of x plus a is the trajectory of the remainder class of x plus a. Right? This is what we want to show. Okay. So these are two trajectories. We can show that they are equal as soon as we show that they intersect. Because the first equipartition property says that two trajectories are either equal or they are disjoint. Right? So to show this, we just need to show that these two trajectories have some point in common. All right, but note that this thing plus this thing is in the trajectory of x modulo n, right? Because the definition of this asks that this be true, right? You are advancing by a. You start at x, you advance by a once. That element should be in the trajectory of x, right? So this is there, but what is this? The way we add things in z mod and z just implies by definition that this is in the trajectory of x modulo n, and therefore these two things intersect, and therefore they are equal. So let me write that down. So thus, this is non-empty, and hence these two things are equal by the first equipartition property, which we just called the equipartition property back then. Correct? So that proves the blue statement, right? Okay, and we have this diagram. Sorry, I meant to expose only that much. So now if you apply the factoring property, because of this periodicity, let me, so because of this periodicity, tau is a function from z to the set of all trajectories. Tau is a periodic function, therefore it factors through z mod az because it has period a. Tau has period a, so it factors through z mod az via the natural projection. This is the language that we use. You have a periodic function, it factors through the corresponding period to give a map tau bar. So pi a is the natural projection. Maybe I'll write it for the umpteenth time. Right here, the remainder class is modulo a, not modulo n, modulo a. Okay. So the factoring property immediately leads to this map tau bar, making this diagram commute. And let me also complete one more thing about this diagram. We could have also drawn with a different color perhaps, z going to z mod nz, and here we have this kind of a natural map. So this is the natural projection, and then what is this map? It picks an element in z mod nz and outputs its trajectory. So in some sense, this could also be written by tau, but then there will be too many taus. Maybe I'll call it tau prime. Right? Just takes an element of z mod nz and outputs the trajectory in which it lies. This, of course, commutes the upper triangle, and the lower triangle commutes by the factoring property. So this whole thing is a commutative diagram. No matter what path you take, there is no confusion, there is no conflict. That's what commutativity means. All right, so far so good. Now, what the second equipartition property says is that the map tau bar is surjective. That's a very simple claim that we will get to. The main point is the fibers of tau bar form an equipartition of the domain of tau bar. The fibers of tau bar, or rather the non-empty fibers, but since tau bar is surjective, all fibers are non-empty. So the fibers of tau bar clearly form a partition because the non-empty fibers of any function partition the domain. We are saying it forms an equipartition of z mod az, meaning any two fibers have the same size. Z mod az is a finite set, so every fiber is a finite set. We are saying any two fibers you pick, they will have the same size. Okay, and as a consequence of that fact, the size of the set of all fibers will divide A. Why is that? Well, how many fibers are there? As much as is the size of this set. Because tau bar is a surjective map, the number of fibers that tau bar affords is precisely the size of the codomain, the target of tau bar. Right? And now any two fibers have the same size. So clearly then the number of fibers will divide the size of z mod az. Maybe I'll write it as the size of z mod az. That will make it more clear. That's more accurate. So this is part of the conclusion. I mean, this is just a corollary of the pink thing, but this is crucial. Anyway, so our main goal now is to just prove that the fibers of tau bar equipartition z mod az, and before that tau bar is surjective. So why is tau bar surjective? Well, note that first of all, this is a surjective map clearly. So I will depict it like this. Surjectivity, when you make a diagram, surjectivity is denoted by double arrows. So this is surjective. Clearly, this is also surjective because, well, the set of all the trajectories is what? I mean, you pick an element, you take its trajectory. So this is clearly surjective. No question about that. So this is surjective. So tau is the composition of two surjective maps, and hence tau is surjective. Great, tau is surjective. And now when you factor out a surjective map, you get a surjective map. This is a purely set theoretic statement. You have a surjective map. If you factor it out via any map, doesn't have to be any, just whatever this might be. I mean, here we can think of it as a very nice map, but it could have been anything. If this diagram commutes, the surjectivity of this is trivial. Think about it. Why is tau bar surjective? Knowing that tau is surjective. We argued that tau is surjective. It's a triviality, but we argued it. And that surjectivity immediately implies that tau bar is surjective simply because tau bar is the composite. Simply because tau is the composite of tau bar and pi of A. The surjectivity of tau along with this equation implies the surjectivity of tau bar. It's a very simple set theoretic statement. Okay, so this part is fine, the surjectivity of tau bar. What remains is to show that the fibers of tau bar form an equipartition of z mod az, that is, any two fibers have the same size. I took my sweet time just to enunciate the second equipartition property, but I don't want to miss anything. Okay, so again, you can skip the lecture now. Yeah, that's probably a good thing to do if this is the first time you are reading elementary number theory. But if you don't want to, great, let's look at the proof. So now we show that any two fibers of tau bar have the same size. Okay, so let's see how to do that. I also don't know. So let's develop a notation as if there were any dearth of notation. So let F0 be the fiber above the trajectory of 0 mod n. Right? It looks like a very heavy object. So F0 is of course a subset of Z mod AZ. We are saying pick or collect all those things in Z mod AZ, which when you apply tau bar to them, land inside the trajectory or are equal to the trajectory of 0 mod n. So that is, in other words, let me say, I don't know what notation to pick. Let me just say this. So this lies in F0 if and only if tau bar of this guy B is an integer. Here B is an integer. This is the remainder class of B. Tau bar of this guy is in or is equal to the trajectory of 0 modulo n, which is same as saying tau bar of this guy is equal to tau bar of 0 modulo a. So note this equation. We are saying that this is equal to that. This is a trivial thing. This is just by the definition of tau, right? You want to figure out what is tau bar of 0 mod a. So you start with 0 here. That becomes 0 mod a when you apply pi a. And then you apply tau bar, you get what you get. But you could have directly applied tau to get what you get. But what do you get if you apply tau to the integer 0? You get this thing. That's the definition of tau. Right? So what is capital F sub 0? It is just all those things in Z mod AZ which have the same image under tau bar as the remainder class of 0. Perhaps a better thing to write here, or a more accurate thing to write here, would have been F sub remainder class of 0. Maybe I'll write it, but that's again a horrible notation. Remainder class of 0 modulo a, not n, but a. Okay? All right. So we claim that for, again, notational problems, let me use alpha and beta. So for alpha and beta in Z, we have these two things in the same fiber of tau bar, meaning this equation holds if and only if this lies in F0. Try to prove this pink thing yourself. First parse it, digest it, and then prove it before you look at what I'm going to say. All right, so proof of claim. So, this equation happens if and only if, by definition of tau, or okay, let me write one more statement. What is tau bar? How was tau bar defined? This, what I'm saying is, instead of writing this, I can write pi a of alpha. Pi a of alpha, this is equal to tau bar composed with pi a of beta. But what is this composite? This composite is tau. Correct? Which happens if and only if, by definition of tau, this happens if and only if the trajectory in which the remainder class of alpha lies, modulo n, is same as the trajectory in which the remainder class of beta lies. And this happens if and only if. This happens if I'll maybe skip one step. This lies in the trajectory of the remainder class of 0. And this is an exercise even though we did it when we were doing the first equipartition property. So just try to see why this equality is equivalent to that belonging statement. Okay? Which is equivalent to saying that the trajectory of alpha minus beta modulo n is equal to the trajectory of 0 modulo n, right? This means that the trajectory of this guy intersects the trajectory of that guy. But if two trajectories intersect, they are equal. So this is in fact an if and only if, of course. So we have that. But this gives, by definition of tau bar, this is tau bar of alpha minus beta modulo A. And that is tau bar of 0 modulo A. Right? That's exactly tau bar of 0 modulo A, and that's exactly tau bar of alpha minus beta modulo A. Which means alpha minus beta modulo A lies in that. Right? So that proves our claim. Okay. And now from that, now the second claim. So now we claim that the fiber which contains the fiber above the trajectory of alpha modulo n, this is nothing but that set. Looks like a horrible statement, but try to see it in a concrete example. All we are saying is that the fiber above this guy is just a translate of the fiber above 0. All the things are just fiber above 0, right? These things are taken from fiber above 0. You translate them, this was supposed to be alpha, right? So you just translate the fiber above 0 by the correct thing, and you get the fiber above the correct thing. Here we have alpha modulo n, and there we have alpha modulo a. Just do not get confused. Right? So why is that? It's actually just a restatement of the first claim, but we will prove this properly. Once we prove this, note that the fiber above alpha mod n has the same size as the fiber above 0 mod n, right? Because all we have done is just translate. So realize that once we prove this claim, we will be done. This will be the end of the proof. Okay, so why is that? Well, proof of second claim. Beta modulo A lies in this fiber above the trajectory of alpha if and only if, by definition, let me modify this. So this is same as saying that beta modulo A is here. This is nothing but tau of alpha modulo A, tau bar of alpha modulo A. Right, because this thing is nothing but tau bar of alpha modulo A. Right? So all we are saying is that if something lies in the fiber of the trajectory of alpha modulo n, then that is same as saying it is in the same fiber as alpha modulo A under the map tau bar. That's exactly what we are saying. So which is to say that this equation is nothing but beta modulo A and alpha modulo A are in the same fiber of tau bar. Right? But now by the first claim, this shows us that beta minus alpha modulo A is here. Right? And now you can write beta modulo A as the sum of an element here and alpha mod A. So maybe I'll use an extra page. YB meager. So this means that there exists something in the fiber above 0 such that this equality holds, which is to say that if we add alpha mod A to both sides, right? Maybe I will write the full thing. Yeah. Sorry, I forgot to add on the left side. So what happened? I just rewrote this statement by adding alpha mod A to both sides. Right? Or maybe I will add it just to be a little bit more notationally sound. I will add it on the left side so that this also, both of these things appear on the left side. But what is this? This is nothing but beta mod A. So there exists something in the fiber above 0 such that beta mod A is equal to that thing. And that's essentially proving this claim. Okay, so I hope I have convinced you of the truth of this, and hence the second equipartition property holds. Yeah, so let's look at the statement again. Right, so we have proven this pink thing, and therefore this green thing holds, which we already argued. Admittedly, this is very complex because of the notation. Now, let me make one remark. In group theoretic language, whenever you learn group theory, this would be just one line. Once one knows group theory, this proof is one line. This proof is a one-liner. There are a few theorems in group theory which you develop, which are very elegant. But since I've unraveled those proofs, it has become this notational garbage, if you will. But anyway, I think it's a good idea to acquaint yourself with the underpinnings of those theorems, whatever those theorems are, in this concrete setting, and then undertake the project of learning group theory. Right? All of these things will connect not immediately. It takes some time. Anyway, so now let's get back to our main project. This is the second equipartition property, but what does it say about inverses? So here we are. Now we can talk about the existence of inverses. So yeah, fix any positive integer and let A be an element of Z mod nZ. And or rather let A be just an integer, as in the statement of the second equipartition property. Okay, and as it was, this is the set of all the trajectories when you advance by A. And again, when I say advance by A, now here A should be thought of as an element of Z mod nZ, which is why I said I should put a bracket here and so on. But anyway, so this is the set of all the trajectories. We claim that this number is a common divisor of A and N. It divides both this and that. Well, why is that true? We already know by the second equipartition property. By the second equipartition property, we know that this number divides A. This was part of that whole package. Why is it that this number divides n? Well, by the first equipartition property, we know that Z mod nz is partitioned by elements of, or maybe I will write it this way. So I'll make this symbol. You pick maybe t from this thing. This is equal to Z mod nz. So what have I written? This thing is just saying that all the trajectories partition Z mod nz. Right? That's part of the first equipartition property. But the first equipartition property also says that any two t's here have the same size. So that implies that the size of any trajectory, I'll just write t naught times the number of trajectories, is equal to n. So t naught denotes, okay, I'll write it. T naught is nothing but the trajectory of 0, or the remainder class of 0. Since any two trajectories have the same size, and since the trajectories partition Z mod nz, n is the product of the set of all the the size of the set of all the trajectories times some number. That number is the size of any trajectory you like. I have just chosen it to be the trajectory of 0. So we have that, and therefore the set of all the trajectories, or the size of the set of all the trajectories, divides n. So we have seen that this is the common divisor of a and n. Okay. And now if we have a positive integer n and a is an integer, then a has an inverse modulo n if and only if a is relatively prime to n. So how does that hold? So here is the proof. The easy part we have already seen. The hard part is when you assume relative primality. So assume a and n are relatively prime. Assume a and n are relatively prime. Then this better be equal to 1. Why is it equal to 1? Well, this is a common divisor of both a and n. Since a and n are relatively prime, and since this is a positive integer, this has to be equal to 1. That's it. So this is 1. Great. And therefore there is only one trajectory, right? Z mod nz is partitioned by the set of all the trajectories, but there is only one trajectory. So the trajectory of the remainder class of 0 is everything. There cannot be two trajectories. There is only one trajectory. So this one trajectory should consume everything. Okay, which implies that 1, or the remainder class of 1, lies in the trajectory of 0. Right? But that implies this is equal to this plus Ka for some k. So I should say for some integer k. And now if you unravel this just means, or maybe I will not skip any step. This means 1 minus 0 minus Ka, or let me do the right side first. The right side is nothing but this. Right? This thing is nothing but that. Because if you add 0 to something, it doesn't change. So the remainder class of 1 is same as the remainder class of Ka modulo n, which means 1 is congruent to Ka mod n for some k. That's it. That means that this thing admits an inverse. A admits an inverse modulo n. Right? So the fact that there is only one trajectory is all. I mean, this is what we saw when we were drawing those diagrams, whatever. So we have proven the main result, and as a corollary, this corollary we stated earlier, that if a and n are relatively prime, and if n divides the product of a and b for some integer b, then n must divide b. We already discussed this and saw the proof of it. Okay, wonderful. And yeah, let's see if there is anything else to say. I don't think so. So that's it. That's the end of this lecture. Admittedly, this was a complex lecture. And as I said, you don't need to follow the proof of the main theorem. In fact, you don't even need to know the second equipartition property. It is enough to just know this theorem. Enough to just know this theorem. When you have some maturity, when you are more comfortable, you can come back to these proofs. And also, as I remarked, when you learn group theory, keep this in mind. Try to see this, or I don't know, try to prove this result using group theoretic machinery. The same proof will be very short because of the packaging. Anyway, so with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.